So taking a look at something from chapter 15, sampling homework. What it says has our molecular mass is 101, and IR we have stretches at 397, 3200, 1655, and 1622. For C13, we have three different types. We have one at 27.5, we have one at 38, and another one at 180.5. So what this tells us is not giving us a molecular formula, but it does give us the molecular mass of 101, so that should tell us something about what we have here. So if we have an odd molecular mass, what does that mean? We have an odd number of nitrogens, that's right. So our nitrogen rule says we have odd number of N. So I'm just going to assume hopefully it's just one for hope's sake. Just for ease, probably. Usually we'll give you the molecular formula. We won't do it this way. We'll just give you the molecular formula. So we know we have an odd number of nitrogen, so presumably it's 1. So that's a no we write to ourselves. We see two peaks at 33 and 3200. That should give us a clue, and this maybe isn't as clear, but we'll go over it more. That's an NH2. That's an N with two H's bonded to it. So this peak right here tells us these two. It tells me, right, it can't just be an OH, because an OH only has one H. So maybe it's two H's, and an N can have two H's bonded to it. So this right here tells me that there's an NH2 bond to something. All right. Peak at 1655. I'm not sure if that's a CC double bond or a CO bond at this point, so I'm not really sure. CO or CC, I'm not sure. Oops. All right, because both of them fall in that range. In 1622, I'm not really sure what 1622 is. Maybe I'm just putting a question mark here. I'm not really sure. Okay. What does the carbon NMR tell us? What's a peak at 180 represent in C13? C double bond O, right? So this tells us, this peak tells us C double bond O. So that, if I go back to my IR, that confirms that this is a C double bond O and not a CC, right? Hopefully that confirms that. The other two peaks, right, tells me I have two different types of I have three different total types of carbons, and I have two other ones. And where were these other types of carbons? What kind of carbons are they going to be?
sp3.
They're both sp3 type carbons. sp3 hybridized. Good. So that's all I know right now. All right? So let's go back to our mass, which is 101. So the two pieces I know I have for sure. I know I have an NH2 bonded to something. And I know I have a CO bonded to something, right? So let's subtract those masses from 101. Right? So a nitrogen weighs what? 14. You will not be allowed to use calculators on the test. If you can't do basic math, you can't do organic chemistry. Right? So that's 787, right? Two H's are 2. That's 85. 85 minus 16, which is an oxygen, is what?
74.
69. 69 minus what is 12 is what? 757. So I have 57 left to play with, right? So presumably all I have left is carbon and hydrogen, right? Because these are both aliphatic, they're both sp3. So if I have 57, it means how many carbons can be in a molecular mass of 57? Carbon weighs what? 12. How many times can I put 12 into 57? 4. 4 times 12 is what? 48. So let's go 48, which is representing 4 carbons, right? So then what do I have? 4, 1, 9. That 9 is probably left over is going to be H's. So I have C4, H9 left over. And I need to have, of those carbons, they have to be 2 types is all. So I can't have 3 types, I can't have 1 type, they have to be 2 different types, right? According to my carbon NMR, 27 and 38. So how could I put that together to get 2 types of carbon? What are the ways I could do it? And they all have to be sp3, hybridized. Split them evenly. What do you mean by split them evenly?
It's 2 carbons will be on one side, 2 carbons will be on the other.
I don't think I can split them evenly because if I have, how many bonds of carbon? Right, I can't split the H's evenly, right? The H's are 9. I can't split 9 divided by 2 is 4.5. I can't have half a hydrogen.
You can't make a double bond.
No double bonds.
Did you just draw a little kink thing?
If I draw a kink thing, like this, and like this, I guess, right? 4. How many? Are all those carbons gonna be the same or different? They'd all be. If I drew it like as I have it drawn here, they have 1, 2, 3, 4.
Different.
And it'd be 2, 4, 6, 9. So this would be C4H9, right? But are all these carbons the same or different? How many different types of carbons does this have? 1, 2, 3, 4. That doesn't match. I only need 2. I can only have 2 types.
Make a bunch of methyls.
I could make a what?
A bunch of methyl groups.
And what would I? So I make a bunch of methyls. So
Like you'd have a carbon and you have 3 methyls coming off of it.
that would be the way I would do it. So if we have a carbon with a bunch of methyls hanging off it, is this still C4H9? So 1, 2, 3, 4. H9. How many different types of carbons are in this? 2. So that works. So now I have my pieces. Now how do I put it together? So now I have 3 pieces, right? I have an NH2, I have a C double bond O, and I have this piece. So the trick is when you have 3 things, and one thing has 2 bonds, right? You put the other 2 things on either side. And you have to check to make sure it matches at the end, though. So does it matter in this case which side I put them on? Because this is the same either way, right?
Yeah.
So what's the final answer going to be?
The C double bond goes in the middle.
C double bond goes in the middle. Got an NH2.
Same.
So there's your final answer. How many different types of carbons do we have? 1, 2, 3. So that matches up. This is at 180 for a carbonyl carbon. We have an NH2, which matches for that doublet in the IR. We have a C double bond O, which matches the IR as well. Does this weigh 101?
Yeah.
Hopefully. Yep. So that matches that too. Has 1 nitrogen, everything matches. Right? But at the end of the day, you always want to go back and check. Right? Go back and check. Another sapling problem from chapter 15. Now on this one they give us C10 H13 NO2. So when you give the molecular formula, the first thing you need to do is degrees of unsaturation. So what is the DU for this? So the degrees of unsaturation is equal to 5. And so what does that tell us? What do we say?
Ring.
Ding, 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 benzene ring. Anything 4 or more, we should be thinking about benzene ring. Why? Because a benzene ring counts for how many degrees of unsaturation?
4.
4, right? 3 pi bonds in a ring, 4. So we're thinking benzene ring. Good. What else are we thinking about here? IR. IR has to stretch at 3285, 1659, 1246. So what do you think about 3285? What could that be? Could be an OH or what else? Right, usually it's not, so usually it's an OH or an NH. If they don't say sharp, then it's not an SPCH. Usually if it's an SPCH, they'll say sharp. So if it's like this, we'll write a note to ourselves, OH, or NH, right? Right, no tricels. What about 1659? What does that make you think about? C double on C or
C double bond N.
yeah, I haven't seen much of that. I would say C double on C or C double bond O, right? Carbonyl or an alkene. About 1246. Any idea?
CO or CO.
What kind of CO? CO single bond?
Yeah.
Maybe it's CO or CN, right? We're not sure. Okay, good. So IR doesn't tell us everything. Like the mass spec didn't tell us everything, or the molecular formula didn't tell us everything, but it gives us an idea. For the NMR spectrum, it looks like this. So I will just I'm just going to write down in word form what it has. It has I'm just going to draw the picture. What the heck? Little fat guy. It has a doublet. A doublet. Quartet. It has a little further down the road. Singlet. Then it has a little further down. That. We're in a little peak at 0. So this is 0. This is 1.2. This is 2.1. This is 3.9. This is 6.8. This is 7.2. This one is 7.5. This is worth 1H, 2H, 2H. J is equal to 9 hertz. J is equal to 9 hertz. And this is worth 2 H's. J is equal to 7 hertz. This is worth 3 H's. And this is worth 3 H's as well. And J is equal to 7 hertz. Okay. Oh, a lot of information here. How many different types of hydrogens are there? How many peaks are there? How many different peaks are there? 6. There's 6 different types of hydrogens. Okay, so I'm just gonna scrunch down that guy. All right, so there's 6 different types of hydrogens. Now we need to go through and figure out what they represent. All right? So we can really start anywhere. And we have a particular place you want to start. Usually, go to the most de-shielded one, or the most shielded one. Let's go to the most de-shielded. So this little fat guy like this, when they're little fatties, that either means an OH or an NH, right? Remember OHs and NHs don't couple, right? So this right here is an OH or NH. We're still not sure yet which matches with our IR, right? So we'll call that one A. B, C, D, E, and F. Okay. So we know A is an OH or an NH. We're still not sure yet which. Who knows? For B and C, let's go to the next de-shielded thing. How many hydrogens do B and C represent? 2 each, right? In what region on your table are these 2 hydrogens? Benzene ring. And there's 4 of them, right? So how many substituents are on your benzene ring? So if I drew a benzene ring, I need to have 4 hydrogens. Now, how many different types of hydrogens do you have in that benzene ring? 2, right? There's 1 type and 2 type. 1, 2 types. So how must the benzene ring be substituted to get just 2 types? So, do I want, if I put one thing is going to be here, right? Where else should I put something else off the benzene ring to get two types? The bottom, right? Completely opposite of it. So then if I draw in these H's, presumably the two things that are bonded to it will be different. So we could say this one is B, and then this one would be C. And would they be coupled to each other? Are they 3 bonds away from each other? Yes. So they have this, notice how they have the same coupling constant? That means they're coupled together. Both of them are worth how many hydrogens? 2, and they're both doublets, so that makes sense. So there's one piece. Good. Let's go to the most shielded thing. Let's go to F. So what is F? F is a CH3. Actually, before I do F, let's do one other thing first. I forgot to do. What I like to do as well is take C10H13NO2. So we knew we have an OH or an NH. We're still not sure which, right? So I'm not going to subtract that yet. But now I know I have a benzene ring, right? So how many carbons is that worth? Minus C6, how many H's? H4. So I have C4H9NO2. Right? Just keeping track and make sure I don't lose anything. Good. So now let's go back down to F. So this is worth 3 hydrogens and it's a triplet. So how many nearest neighbors must it have if it's a triplet? 2. And usually a CH3 like this, if it's 3 H's, I always think CH3. So a CH3, and that's F, right? And who is F coupled to? D. Why did you know that? Same coupling constant. So D is how many H's? 2? Do you know what's on the other side of D? Me either. So now let's subtract out this piece. So this is worth C2H5, right? So we have C2H4NO2, right? So we've used 4 of our degrees of unsaturation. We're still missing one of our degrees of unsaturation, right? Because this is worth 4 and we have 5. So we probably have, right? And we already know we have a CO or a CC pi bond somewhere, right? Good. What about this singlet? What's that going to be? E.
3 carbons.
That's a CH3, right? Does it have any nearest neighbors?
No.
It does not. And that is E. Right? So then we subtract out a CH3 here. So a C, an H, an N, O, and a 2. Right? So at this point, you should probably know we have a carbonyl, C double bond O. It's going to be hard to have a CC pi bond with only 1 carbon, right? Yeah. So we could probably say one of these pieces is going to be a CO at this point. So we know it wasn't that, it was this. Right? So we subtract out a CO. So now you have HNO left over. So now it's hard. How do you know if you have an NH or an OH at this point? Let's look at one of these. So let's look at the frequencies now. At this point, the last thing you kind of do is look at the frequencies. This one's at 3.9. This is pretty de-shielded. Do you think it's going to be next to an oxygen or a nitrogen?
Oxygen.
Oxygen, right? Why? Oxygen is more electronegative. So next to D, I'm going to put this as being an oxygen now. Right, I know it's getting kind of messy. These things were doing what I want, but they're not. Got me so far, hopefully. Okay, so I decided to put the oxygen next to D because this is so D shielded at 3.9. So that means I have what instead? So I've used my oxygen, so minus O. We're gonna have an NH somewhere, right? So we have to have an NH bonded somewhere as well. So how many pieces do we end up with? We have a benzene ring, we have an NH, we have a carbonyl, we have a CH3, CH2O, and we have another CH3 over here. This CH3 over here is what frequency? E is at 2.1. Look at your table. Where's 2.1 at? Allylic, right? So that should be where do you think you want to put it?
Next to acetyl bond.
Next to acetyl bond O. So let me start building this. So this will be HE over here, right? Everybody with me for that? So I don't know what's on the other side there, but I've checked this off and I've checked this off. So now I have 3 pieces left. Well, 4. I have the benzene ring, the NH2, and this OCH2 CH3. So now let's see if you can put it together. Okay, so the final piece to put this together, this NH2 needs to go right next to the carbonyl. All right, so the question is, I know I have to have, this has 2 spots open, this has 2 spots open, and each of these is 1. The trick here is, have you guys ever seen me bond oxygen and nitrogen together yet? No. So if it looks weird, you've never done it before, it's probably not right. Right? So the final answer would be, if I move everything out of the way here, I'm just going to zoom in. Nope. Maybe not. Benzene ring. This is HE, right? Singlet, 2.1. NH is that fat little guy, was proton A. This is either B or C. Doesn't matter, you don't need to decide which one's which. I'm not asking you to do that, but B and C are there. CH2, next to the oxygen is HD. CH3, farther away, HF. So this is your final answer. Right? So a lot of times at the end of the day, you've got to put your pieces together and make sure it makes sense. Right? This would be, it says 2 nearest neighbors, so this should be a triplet. It's a triplet. This has 3 nearest neighbors. It should be a quartet and D-shielded. It is. Those 2 are coupled together. CH3 in the right spot. Double it and double it. Right? Carbonyl carbon makes sense. A CO, IR stretch, C-double bond O. It all makes sense. Right? Double check and make sure. This one, it says the mass spec has an M+1 peak equal to 115. So remember, M+1 means you've added 1 to the normal mass. So what's the actual mass of this molecule? M, which would be in this case 114. So the actual M plus peak is equal to 114. So that's what we really care about, right? So an M+1 peak means you've took the normal mass and added 1. So this thing weighs 114. Does that mean, does it have any nitrogens? It could, right? It could either be, it's an even number of nitrogens. Remember, 0 is an even number. So it's probably 0, usually. IR, it says we have a stretch from 3,000 to 3,580 that is broad. Right, so that's interesting. We just talked about that. We have a peak at 1698. And then another one at 981. So I want to go look at our IR tables and see. So what do you think the broad 3,000 to 3,580 is? Some sort of OH. Maybe a carboxylic acid. What about 1698? What's that telling you? CO stretch. Good. What about 981? What about 981? It's a very specific stretch. And it's in that table. Alkene. What kind of alkene specifically?
Trans.
A transalkene. Good. Look on that table 13.4, 13.5.
Says 960 and 980,
Yep.
so it's okay.
I'll be better on the. It's an approximation. Take my word for it. I'll make sure on a test or quiz it's always in the range, but reality is not always perfect. Good. Everybody with me so far from the IR? So that's a lot, right? That's a lot. So let's subtract that from 114. So 114 minus OH is what? OH is 17. 97. Carbon in a carbonyl is 16 plus 12, which would be 28. So you see 9. And then the transalkene is 2 carbons, 24 plus 2 H's is 26. So that's 3 and 43 left over, right? And this is before we haven't even looked at the NMR yet. There's a whole NMR spectrum for this. We haven't even looked at it yet. Right? So what's 43? How many carbons is that going to be? 3. C3, and then how many H's? Yep. H7, right? That's what we have left over. Before we even got to the NMR.
And you just know that by combination of them weights and masses.
Yeah, so how did I get to C3?
Yeah.
I just took 43 divided by 12.
How do you know that it's only CH?
I'm hoping it is. I've seen 43 as a fragment in mass spec before, so
Okay.
ideally I would, right, this is the problem with all these problems. At some level, no one runs an experiment where they don't know what they're starting with. Right?
So like on the test, you'll give us the formula.
I'll give you the formula in the test. Yeah. Right. So this is good practice. All right. C3H7. So, and I mean, once you see the NMR, you'll know more, right? Okay, so we're here at this point. This is just after the mass spec and IR. Good. So let's shrink this stuff up for a second, and I'm going to draw the NMR out. So I have the spectrum drawn, NMR spectrum all drawn in here, but I wanted to highlight one more thing I forgot to mention. There's a UV stretch. So this compound is UV active at 212 nanometers. So what does that tell us about this compound? If it's UV active, what does that tell us? Has conjugated pi bonds, right? So it has conjugated pi bonds. And that's what it's telling us. Good. So the first part I would do here is there's 1, 2, 3, 4, 5 different types of peaks. The number of hydrogens they account for, and the coupling constants they have, right? So E has 1 coupled partner. D has 1 coupling partner. C has 1, 2, 3 coupling partners. B has 1, 2. A has 1, 2. Okay? What I would do first is say who's coupled to who, right? So A is coupled to B, and it's also coupled to C. B is coupled to A, and it's also coupled to C. C is coupled to A and B, and either D or E. It can't be coupled to both. But if you look at E and D, they must be coupled to each other, so C must be coupled to D. Right, because E can only have 1 coupling partner. So there should be another coupling constant. Yes, there should. So I would have amended this question and added there's another coupling constant at 7.4 for D. There should be 2 coupling constants for D. Has to be. Has to be. Okay. So let's just do the first one. So from our IR we knew, right? No benzene ring, right? But we know we have an alkene, right? We have 2 as transalkene. So A and B must be those things, right? But it looks like one of them is pretty de-shielded, right? One of them is even farther down than normal. What's the normal vinyl region? It's from, vinyl region is usually where? 4.5 to 6.5, but this one's way down at 7. So it must be next to something that's de-shielding, right? So if I draw this piece, I say, okay, this is A, and this is B, right? A must be near something that's pretty de-shielding, right? Or actually they probably both are, right? They both are. So what could that be at this point? What do you guys think we have? What's the other functional group we probably have in this molecule? A what? An OH, but what kind of OH? Carboxylic acid, probably, right? C-double bond O, right? We got to count for that C-double bond O somewhere. And we see that broad range like that. So let's put a C-double bond O over here. Right, that's going to be electron withdrawing. So that's everything we knew from the IR. Now we just kind of put it in place to make sense with A and B, right?
Matters because A is more shielded.
A is more de-shielded because it's closer. Yeah, so A would be more de-shielded because it's closer to the carboxylic acid. I forgot there's another peak in the IR, or the NMR, my bad. There's a peak at, they're showing a little fat guy like this at 11.9. So what would be at 11.9 that's worth 1H? An OH from a carboxylic acid, right? If you look at your table? Yes? So that confirms that we have a carboxylic acid. That's the other piece to make sure we know we have a carboxylic acid. There's another NMR peak that I just forgot to mention. Right, it's broad. Right, if it was an aldehyde, it'd be sharp. But since it's broad, right, since it's kind of fat like this, we know it's an OH from a carboxylic acid. Okay. So now we're done down here. Let's go back. I like to go back to the shielded end. So we have a CH3, right? So what's that look like? How many nearest neighbors does, if I draw a CH3 in and make that E, how many nearest neighbors does E have? It's a triplet, so it has 2. And who is E coupled to? According to the coupling constants, who is E coupled to? D. And according to the coupling constants, who is D coupled to? How many hydrogens is C worth? It's 2. Have we covered everything?
Wait, so how did you decide that E was the methyl based on
So,
the range?
I knew E was the methyl because it was a CH3,
Oh, okay.
right? And then I said, okay, it's a CH3 and it's a triplet. How many nearest neighbors must it have? 2. I also knew the coupling constant, so it must be near D. And D is coupled to E and who else? C. So that would go here then. And then what's the last place I could put this? This needs to go here, right? So the final product is what? It is had to have a trans-double bond. Remember we talked about that from the IR? And that's our final product. Interestingly, so if I said this is E, these are D, C, B, and A. Remember the N plus 1 rule? How many bonds away do you have to be? Less than 3. Is A talking to C somehow?
Yeah.
It is. How many bonds away is A from C?
It's not.
4. It is 4, right? 1, 2, 3, 4. So even though they're 4 bonds away, sometimes they can talk to each other. Notice how this coupling constant is really small? Or is it N? Or it's 7.0. Sorry, no, I'm wrong. One of these is talking to each other. Maybe I have A and B wrong. I have to switch those around.
A and C.
B, nope, A and B need to be switched.
Yeah, okay.
I wouldn't worry about it. Don't worry about it for right now. If you did even the way you did it, there's only one way these have to come together, right? So it really doesn't matter what A and B are. So there is a little more complication here that you can actually be more than 3 bonds away and couple, but it really doesn't matter. You don't need to know that for this problem to make it work. We can talk about it more later at a different time. Go. All right, another chapter 15 sampling problem. This one says EI mass spec, 2 molecular ions of equal intensity at 180 and 182. So an M and an M plus 2 peak, an M plus and an M plus 2 peak. Equal intensity. So what does that tell you? What does this molecule have? This molecule has a bromine, right? Because the bromine isotopes, 79 and 81, exist in a 50-50 ratio. So we know we have a bromine. Nice. The IR tells us 1740. Whoops. So what is at 1740? C-double bond O. What type of C-double bond O?
I thought that it may be an aldehyde, but I wasn't sure.
What else could it be? Aldehyde, you're saying?
Ester.
Or ester. Right? Aldehyde or ester. Right? So the NMR will tell us if we have an aldehyde or an ester, right? Aldehydes in NMR show up where? Where does the H in an aldehyde show up in an NMR?
Oh, and those weird 2 peaks.
That's the IR peaks.
Oh.
So we would, yeah, so that's the other thing. If we had an aldehyde, don't you think they would tell us those 2 peaks at 2820 and 2720? Probably. Or maybe they didn't, fine. But in an NMR, where would the H be from an aldehyde at in an NMR? What frequency? What ppm? Really de-shielded, right? Remember the diamagnetic anisotropy? It'd be around 10. So if we have an aldehyde, we should have an NMR peak at around 10 or 9, right? We don't. So I'm guessing, not guessing, I know we have an aldehyde. So now I'm making that piece. We have a bromine somewhere. Nope, I lied. We don't have an aldehyde.
Okay.
I know we have an ester because I don't have the aldehyde peak. So I know I have an ester somewhere. Right? This is just from the IR. So let's take 180, subtract 79, that's what bromine weighs. Right? Bromine 79 does. What is that? 101? Yep. 2 oxygen weighs what? 32? 1, 9, 79. Carbon weighs what? 12? 7, 67 left over. So now you have 67 left over. How many times will 12 go into 67? 5? Everybody agrees? So 5 times 12 is what? 60. So we have C5, H7 left over. Yep. We have 2 pieces, a bromine and an ester. So now let's look at the NMR. The NMR has, I'm going to draw it in here. Okay, so I went ahead and wrote in the NMR. This is what the house given to you. So how many different types of H's do we have in this? 4. So let's label them. A, B, C, and D. They all have the same coupling constant. Does that mean they're all coupled together? No, it's just a coincidence they all do. So presumably they're paired up, right? So the trick is going to be to figure out how they're paired up. Well, it's not that big of a trick, right? If you look at A, so let's look at A. A is a triplet, right? How many nearest neighbors does A have? 2. Which other proton that we've labeled is worth 2 H's? C. So probably A and C are combined, right? This A, if A is a CH3, we know A has to have how many nearest neighbors to be a triplet? 2. Right? And what would those neighbors, and then C is the only one we have that's 2. And now see if this makes sense for C. C needs to have how many nearest neighbors? 3, because it's a quartet. Does this make sense for C? So that makes sense for these 2. So let's check those 2 off. Okay? I don't know how that happened. presumably that means B and D are coupled together, right? So B is what? B is a CH3. And it's split into a doublet. So that means it's coupled to D. Would that be 1H, right? And D is split into a quartet, so it needs to have how many nearest neighbors? 3, right? Do I know what else is on here? No, I know it can't be hydrogens. So that checks off those guys. So now you have all your pieces. Now it's just a matter of putting them together so the frequencies make sense. So if you look at HC here, right, HC, it needs to be where? Well, there's an ester and there's a bromine. Right, what are my 4 pieces? I have a bromine, I have the ester either side, I have 2 spots here, and I have 1 spot here. So start putting things together and see what you can come up with. And then check back to see if the frequencies make sense. Okay, so there's really only 2 options that can go together. So you can have C, HB, which is next to HD. You can put the bromine here, and put the ester here, and put the other piece there. That's one way you could do it. Or you could do it where here's your ester, like that. Now, which one makes sense with the frequencies we have? Which one makes sense with the frequencies we have? So your 2 options essentially are flipping around the ester. So in this case, HC is supposed to be at 4.23. But as I have it drawn here, where would HC be at? What frequency would it be at on your table? 2.5-ish, 2.1, something like that. But that's not where it needs to be, right? For C to be 4.23, what does it need to be next to? Something electronegative. So it has to be next to this oxygen. This HD is already going to, the bromine's there. So it's really going to de-shield it already, right? We need to make sure C is next to the oxygen, so it becomes de-shielded as well. So that's the trick, and that's the answer.
So you know it has bromine.
I knew it had bromine from the mass spec when it told me it had 2 equal intensity peaks at 180 and 182. That tells me M and M plus 2, so yeah, I knew it's either bromine or chlorine. And because they're equal intensity, I knew it was bromine, because bromine's 2 isotopes are a 50-50 mixture. Chlorine is 75-25.
So off like the bromine, like the carbon and bromine, you have the.
So this is D
Yeah.
and this is B, those H's. That's right. So go back and check now. Does it all make sense? The coupling makes sense. Now the frequencies make sense. That's good to go. Right? So you can come up with 2, right, answers, but then you have to go back and check, right? Go back and check. Does this make sense for HC? It didn't. This is not de-shielded enough. Right? Use your tables.